right? And we were talking about Andromeda galaxy. So that will be the largest galaxy in our local group. Okay, so the Milky Way belongs to the local group, and we will get back to this. So it's just an introduction. But Andromeda galaxy is the largest one, and it's coming toward us. And the point of this slide is for you to understand that light years is a unit. The light year is a unit of distance. So Andromeda galaxy is about 2.5 million light years away. So we see it as it was 2.5 million years ago. Okay, because it takes 2.5 million years to reach us. The image that the light will carry will take 2.5 million years to reach us. Okay, so light year is a unit of distance. It's a distance traveled by the light in 1 year. So light goes really fast, but still it has a finite speed. Okay, and I told you that the universe is expanding as a whole, but if you look at local structure, like the local group, galaxies can still go toward each other. So the Andromeda galaxy is supposed to collide with our own galaxy, but don't worry, that's not going to happen before 4 billion years from now. And even when it happens, it's mostly void. Okay, the distance between the stars are humongous, so they will just pass each other. Only the gas will collide with each other. We might not be even around. Okay, just to make sure, because that's always a question. I don't know which test or if it's a final. Nothing can go faster than the speed of light. Nothing. It's the law. It's not possible. Good morning. Nothing can go faster than the speed of light, except the universe itself. So it means just after the Big Bang, we think that the universe was expanding, but faster than the speed of light. That will explain why it's so homogeneous all the way around, right? So if you look at the universe, like from far away, if you look at very, very, very far away, you look at the baby universe just after the Big Bang, and it's quite homogeneous because after the Big Bang, it was expanding, but super fast. So you didn't have time for diversity to happen. So remember that nothing can go faster than the speed of light, except the universe itself just after the Big Bang. Okay, so the other thing that you need for the pop quiz, I don't know if you remember, on the Monday we watched a video and the video went through a galaxy named M87. That galaxy is part of the Virgo cluster. So it's another cluster of galaxies. Okay, you have the local group where our Milky Way is, and then you have another cluster of galaxies called the Virgo cluster. At the center, you have the M87 galaxy, and at the center of that M87 galaxy, you have a supermassive black hole. And why is it such an interesting case? It's because for the first time in 2019, they were able to take a picture of this black hole. Okay, so of course you don't see here, it's a black hole. So black hole, right? You cannot see it because nothing can escape a black hole, not even light. But what you see here is some plasma, okay, some gas going around the black hole and being fed to the black hole, and it's going to radiate in radio waves. So you can see that. So that's a supermassive black hole. That was a picture taken. I will go back to that by a telescope, Event Horizon Telescope. Okay, so I just want you to remember this one. So 2019, they took for the first time a picture of a black hole, supermassive black hole. So we think that at the center of every single galaxy, there is a supermassive black hole. There is one at the center of our galaxy. So in 2019, they didn't have the resolution to get a picture of our own black hole, but in the meantime, they did. So we do have a picture of our own black hole at the center of our own Milky Way galaxy. Isn't that exciting? 2019, it's not that long ago, right? Okay. What else? Okay, so I'm just introducing the topics, right? Okay, so don't panic. I'm not going to go into details. I'm just introducing. So then, after talking about the scale in the universe, so that will be our first unit here, unit 1, 1.2. Then unit 2 will be about history, because, Newton, who was a genius, he was a sociopath. He was not a very nice man, but he was a genius nevertheless. And he had a very high opinion of himself. And he said, if I have seen so far, it's because I'm standing on the shoulder of giants. So we will talk about those giants, including beginning with Copernicus. Okay, so Copernicus was Polish, and he's the one who challenged the geocentric model. So before Copernicus, they were convinced, and it's also for religious reason, that because man is made at the image of God, so the Earth has to be at the center of the solar system. So this is called a geocentric system, the geocentric model. So the Earth here is at the center because we are so important here. And the sun orbit the Earth, and the other planet orbit the Earth as well. And then Copernicus said it doesn't make sense based on observation, and he's the one who introduced the heliocentric system. So helio is sun. Okay, in Greek, I think it's in Greek, Helios. It was the god of the sun. So anyway, he introduced the heliocentric system, but he was very, very careful. You have to be very careful of what you say, right? So at the time, he didn't want to be in trouble with the church, so he waited to die. He waited to be on his deathbed, okay, to say it in the book, very famous book, right? So anyway, that model was then picked up by Galileo Galilei, that you all heard about, and then on those shoulders stand Newton. So we talk about Newton. He's a father of gravity. He came up with this understanding that you need a glue to hold us to the earth, so that will be gravity, to make an apple fall on the earth, so that will be gravity, but also to glue the planets to the sun to the Milky Way to the other galaxies to the other cluster of galaxies, and so forth and so on. So he came up with gravity. Okay, we'll talk about Johannes Kepler and Tycho Brahe as well. So that will be for unit 2. If you have any question, let me know. I might not be able to answer everything, but I will get back to you. The idea of this class is for you to like and enjoy astronomy. I don't need to cover any curriculum, right? Can take my time. Okay, so then we'll talk about constellation. I have shared with you that someone shared with us free app that you can download in your phone. And I told you that even though most of you take this class because it's a requirement for your major, take benefit of it, right? Get the most that you can get from it. Meaning, if you start observing the sky, okay, and it's not that hard, then it can boost your resume. Okay, if you start to attend those Saturday night observation sessions at MMC, you can talk about it in your application. Okay, so just suggestion, you just do whatever you want. Okay, so we'll talk about constellations. So that will be the constellation you are expected to see in the northern hemisphere. So what you see here, this star is Polaris, the North Star, okay? And it's going to show you the north, right? You have the small dipper, but you cannot see it with the naked eye. And here you have the Big Dipper that you can see with the naked eye, okay? And you have the other constellation as well. Jupiter can be seen tonight. And let's see. Okay, so you can look at them. So we'll talk about that. Then we'll talk about what I call tools of the trade. So everything we know about the universe, about the stars, about the black hole, how the universe is expanding and even accelerating. It's not that we are able to go in space and, I don't know, bring back a star and cut it open. Everything we know about the universe is because we collect light. So light is the great informant. Okay, so using sensors in telescopes, space telescopes or telescope on Earth, we collect light and we analyze this light. So in science, this is called spectroscopy. And maybe you have done those experiments in high school in chemistry. Usually it's done in chemistry where you have some flame with a compound inside, like sodium, and you look at the light through a prism, and the light will be decomposed into its color or wavelength. And by looking at this rainbow that you get, and then you have some black lines superimposed to it. It's like a QR code. By looking at this QR code, you can know what's in that flame. Okay, what's the component. So, for example, it can be used also in industry. If you are looking at a chemical power plant, for example, and you are not sure if they are doing something legal or not legal, right? You can look at the smoke with this prism, okay? And by looking at the spectrum and this QR code, you can tell, are they using mercury, for example, okay? And they are not supposed to. So you can use that science spectroscopy not only in astronomy, but physics and chemistry, environmental science. Okay, so that is the James Webb Telescope that was launched in 2021. Let's see if I have a, and it has a very, very good resolution, amazing resolution. It can see, is able to see not only in visible light, but also in infrared. Okay, so that means we can see really what's going on just after the Big Bang. We can see the baby galaxies thanks to this telescope. So the amazing piece of technology. Just as an introduction, let's see if I have a picture. So this is the James Webb Telescope. And
now to some new pictures that have been released by NASA showing our largest planetary neighbour, Jupiter, in unprecedented detail. They come from the new Super Space Telescope, the James Webb, and they show moons, rings, and storms in what astronomers have called incredible detail. Here's our science correspondent, Helen Briggs. Jupiter in a whole new light. The famous Great Red Spot, a storm larger than Earth, visible as a radiant white dot. Glowing light shows or auroras dancing at the poles. Faint rings and two of the planet's many moons standing out against a backdrop of glittering galaxies. Scientists say these stunning new images, artificially coloured to make the features stand out, are better than they could ever have hoped for. These images are so much more than just pretty pictures. Yes, they are pretty.
okay, so James Webb Telescope, right? 2021. And I forgot to show you last time that I have a very nice, so I try to show you some video that I have collected over the years. So this one I think is very nice. It's called Our Place in the Universe. So I forgot to show it. So the resolution of the projector is quite bad. So that's why here I have another computer with a better resolution. So I don't know, it's very hard if I can share with you. So maybe it's better. I don't know. Maybe you can move. Maybe this is fine, it's fine with me.
Since the Big Bang, the universe continued to grow and expand. To understand just how big it has grown, we need to take an imaginary spaceship ride from the Earth to the edge of the visible universe. Our nearest neighbor is the Moon, just 250,000 miles away. At the center of our solar system, 93 million miles away, is our Sun. Crossing the center of our solar system, we continue our flight beyond the orbit of the Earth. The next planet out is Mars. Beyond the orbit of Mars is the asteroid belt. A billion miles away is the giant outer planet Saturn, almost 1,000 times the size of Earth. As we leave the solar system, we would pass one of our earliest interplanetary explorers, Voyager 1, launched in 1977 and traveling at a mere 40,000 miles per hour. Proxima Centauri and Alpha Centauri, A and B, our nearest stars, are 25 million miles away. Our solar system sits in the quiet suburbs of a spiral galaxy, the Milky Way, a star city containing over 100 billion stars. Every star we can see in the night sky lies within our own galaxy. This is deep space. Out beyond the Milky Way, 10 million miles from Earth, is the next spiral galaxy, Andromeda. Even traveling at the speed of light, it will take 2 million years to reach here. Andromeda and the Milky Way form part of a small cluster of galaxies called the Local Group. But stretching out way beyond the Local Group are much greater clusters of galaxies. If it were possible to travel fast enough for long enough and reach the edge of the known universe, this is what we would see. Uneven clusters of galaxies, a pattern that was predetermined in the very first second of the Big Bang. This is as far as our spaceship can take us. We are now 50 billion trillion miles from Earth. This is where science ends and speculation begins. Astronomers may never see what lies beyond here. This is where the secrets of the universe are hidden.
Okay. What I want you to understand is that if you attend the class and if you come on time, this class is a breeze. Okay, it's an easy A, but you cannot space out. Although spacing out for an astronomy class is not that bad, but if you really pay attention, you don't even need to review for the test or for the assignment. You just need to use your listening ears and not going on your phone or laptop or whatever you are doing. Right? If you really pay attention, it's just 1 hour, so it's 2 hours a week, so it's not that much. Pop quiz is fun because then you get to know, new friends, right? You can make connections. It's an introductory class, so it's not that hard. I have wiped out all the math, okay, because that didn't go well with students. So just pay attention, arrive on time, and it's an easy class. I still get D, and C, but if you pay attention, you get an A. Okay, so that's just a parenthesis here. So then the next unit will be about the solar system. So I'm not going to go really deep into this topic because there is another introductory class about the solar system. I think it's introductory, so you can take this other class if you want. Right? So we'll talk about solar system and one AU. It's called the astronomical unit. So it's a distance between the sun and the Earth. So that will be about 93 million miles. So that's a big distance here. And as you all know, the Earth is revolving counterclockwise. Okay, so this is the north and that will be the south. So from that view, Earth is going counterclockwise, and you see it has a tilt. So typical question on the final: why is it hot during the summer and cold during the winter? So they have asked this question even in Ivy Leagues, right? They went to Harvard and they say, why do you think it's so hot during the summer and cold during the winter? And most students said, even from Ivy League, they said, oh, because during the winter, the Earth is farther away from the sun, and during the summer, it's closer to the sun. It's actually the opposite. So why do you think, for example, here that will be winter and here that will be summer? How come it's so hot during the summer? What do you see? The difference here. The tilt, right? So you see during the winter, Earth is tilted away from the sun, and during the summer is tilted toward the sun. So if this is the sun, I'm tilted toward the sun, I'm going to get more radiation. That's the reason. So typical question. It's a conceptual question, right? But most, if you ask the question around you, most people don't know. So we'll talk about the solar system. So the solar system is not just the sun and the planets and demoted Pluto, which is totally unfair because you see here Pluto sometimes is going closer to the sun than Neptune itself. So very unfair. Sometimes it goes through what we call the Kuiper belt. Okay, so farther away you have this donut shape structure. It's made of junks, orbiting the Earth, and among them you do have like planets, right? Like spherical objects orbiting the Earth, orbiting the Sun. So this is called the Kuiper belt, and it's not just that. Okay, if you zoom out a little bit more, you have what it's called the Oort cloud. Okay, so you have the solar system, you have the Kuiper belt, and then you have even more junks. So all these here are glued to the sun because of gravity. So the solar system is not just the planet, it's the whole thing here. So sometimes you have an object here visiting us, like a comet. It's going to take thousands of years to make the orbit here, right? And sometimes the comet will come back, sometimes it doesn't. Sometimes you have a comet coming from the Kuiper belt here. So it's not only just the planets, it's the Kuiper belt plus the Oort cloud. Okay, so just an introduction. So it takes thousands of years for a comet uh, to complete its cycle if it comes from the Oort cloud. Okay, and then we'll talk about catastrophic collision. So when you have an object hitting the Earth, that will be called a meteorite. A meteorite could be an asteroid that will escape, or it could be a comet that will be pulled by the Earth. So most of the time, we don't have to worry about them because of the atmosphere, right? So when something is trying to aim at the Earth, you have so much friction that it will evaporate. Okay, it will turn into gas, but times to times it will be big enough that not everything will disappear and it will hit the Earth, right? And times to time, if it's really big, it can wipe out life on Earth, right? So, for example, 65 million years ago, we had a meteorite hitting the Earth, and everything was wiped out. Almost two-thirds of life was wiped out, including the dinosaurs, which is good for us. So it will be very hard to go to school if you have a dinosaur chilling out. But not only the dinosaurs, other animals as well. And sometimes in places on Earth, you can find the remnant of that meteorite. Not this one, not the one that killed the dinosaur. Here, it's another meteorite that you can see. You can see the remnant here in Arizona, and it's called the meteor crater. And you can see this is the road. Okay, so this is the visiting center. So it's really huge. So that happened 50,000 years ago. So typical conceptual question, why do you think it's still around? How come we can still see it and we don't see it in Florida, for example, or other places in the US? What's so special about Arizona? Is it humid like in Florida? Right? It's a dry climate, right? There is no erosion, there is no rain, there is no snow. There is so it's very well preserved. So, you can go there and visit that crater. So, anyway, time to time, there is a meteorite that will hit the Earth and it has its name on it, right? It has Earth, right? So, it's going to hit the Earth and it can cause a mass extinction. So, that will be one of the units. It could be asteroids. So we have asteroids between Mars and Jupiter. Okay, it's not only, but a lot of them around Mars and Jupiter, and they look like potatoes. So that's a small potato here. It's an asteroid, and it has its own tiny itsy bitsy moon, little dot here. Okay, so that will be also one of the units. And then we will talk about the formation of the solar systems, which is called the nebular hypothesis. And then in 1992, for the first time, they did spot the first exoplanets. So planets outside our solar system, but inside our Milky Way. And that was done by this amazing telescope. Now it's broken. And they didn't fix it because now they have new technology, so they have cheaper way to make radio telescopes. So this is a radio telescope. Okay, so it's collecting radio waves from space, and it's called the Arecibo Radio Telescope. So Puerto Rico. So you see here you have the tropical rainforest around, and it was broken in 2020. Yes.
So you don't actually like magnify an image on that, but it's like a radio based?
Yes, yes. So in that case, yes, we do have picture of exoplanets, but not at the time. But they are very rare. But we do have them. So in that case, they were able to detect them. So we'll talk about how do they detect exoplanets, but they detected them using radio waves. So what's happening? It was very surprising, not expected. So first of all, those exoplanets were detected around a pulsar. So a pulsar is not a star in the sense that it's burning fuel. It's dead. It's done. Okay, and it's a remnant. It's a corpse. So after a massive star explodes, there was a big explosion, a supernova. What will be left behind could be a neutron star. So it's a neutron. There is no more fusion. And around that star, they found 3 planets. So how did they find it? It's because the pulsar pulls on the planet, right? So the pulsar was wobbling a little bit because of the planet, and that's what they were able to detect. So they detect the radio waves here, burst out by the pulsar, and because you have 3 planets orbiting the pulsar, the pulsar, Newton's third law says if for every action you have a reaction. So if the pulsar is pulling on the planet, okay, so the planets are orbiting it, the planets are cooling on the pulsar. So they could see a difference in the radio waves generated by the pulsar. So it's an indirect method to detect exoplanets. So anyway, I will explain more, but it was very surprising because there is no way those planets could be born with a star that will later exploded as a supernova. It will have been destroyed. So we don't know how those exoplanets ended up orbiting that pulsar. So they think that maybe, those planets, they had no host star, they were wandering around and they were trapped by the pulsar. So no way there is life. You cannot have life in those conditions. This is a horrible star. It's been very fast and it's burping out not only radio waves, but it's also burping out X-rays and gamma rays. So it's not possible for life to survive. I don't know if I have a picture. You have the pulsar and 3 planets. So that was the first time they were able to detect exoplanets or other planets, right? And then in 1996, for the first time, they were able to find exoplanets around a star like our sun. 1996. So it's not that long ago. And then since then, they have found thousands of exoplanets, including Earth-like planets. So the search is for life, right? Will it be possible for life to evolve on those exoplanets? Okay, and then we talk finally about stars. So inside the star, uh, start with a nebula, so a cloud of dust and clouds, and somewhere maybe there is a supernova, so that will provide a kick. There's a little kick here. You need a little kick. So all those dust and gas start to be squeezed, right? Because of the kick and gravity is taking over, so it's squeezing, right? And if the squeeze is the pressure and the temperature is large enough, then a star is born. So in summary, you can have small stars, okay? So those small stars will burn their fuel very slowly. So small star means a small mass. So it's not being squeezed too much by gravity. So it will burn its fuel, hydrogen into helium, very, very slowly. So, for example, that will be our sun. It's going to burn hydrogen into helium for 10 billion years. So we are half of it, right? We are done with 4 billion years. We have 5 billion years to go. And then at the end, when it's going to run out of hydrogen, it will start burning helium into carbon and oxygen. And at the end, it takes 10 billion years, so it's a long time, a long life. At the end, it will burp out its outer layer, but very gently. It's like a cosmic burp, right? Nothing as a supernova, and it will become a white dwarf. And that will be determined by its mass. Now, if you have a small mass, it's like playing with Play-Doh. Depends how much Play-Doh you start with. If there is not enough material here, you can make a small star. And so it means that it's not being squeezed very hard. So it's going to burn the fuel very slowly. It has a very slow metabolism and it's going to live forever, like trillion of years. And that will be called a red dwarf, right? So it's like the greedy people, they don't like to spend money, they go very, very slowly. Or think of metabolism like when you are young, you have a high metabolism. And when you get older, you get insulin resistance and you have a low metabolism. Same thing with star. And then if you have a big, massive star, they get more squeezing because of gravity. So more mass, more gravity, more pressure. So the fuel is going to burn very, very, very quickly. The metabolism is on steroids. And those stars maybe will last only 1 million years or 100,000 years. So they have a very short life. And they go as a supernova. At the end, you can have a neutron star or black hole. So what we say about star is live hard and die young. So it means if the mass is big, metabolism is high, the rate at which the fuel is burned is very quick. So, okay, they will have fun, but they will die young. Okay? Inside the star, you have fusion inside the core, hydrogen burn into helium, and that will burp out energy. So this is called fusion. So if you read the news, because some of you, maybe you are in politics or interested by what's going on in the news, they talk about fusion a lot, especially now. So it's been like 20 or 30 years that they are trying to have fusion under control. Okay, so for example, if you take a nuclear weapon, hydrogen bomb, this is it. You turn hydrogen into helium to summarize, but it's not under control. So what they are trying to do with fusion is to have it under control. You can get a huge amount of energy and you don't have waste product. But they say always, oh, we are almost there. Oh, we are almost there. I don't know. I'm still waiting for that to happen. They are able to do it, but it's still not very efficient. And why are they so much after energy? They want to find a way to produce energy at a lower cost. It's because of AI. AI is a big energy consumer. So they put money into fusion fighter. They get millions of grants to those universities who study fusion. So anyway, that's a tangent. So let's go back to our business. So very famous quote, live hard, die young. And just because I like to connect to American culture, it was a very famous song in the 1950s. It was a hit. Not that I was born in 1950, okay? Don't believe that. Hopefully. But it's a very famous song. And then the song will stick to your head all day. Okay, you can listen on your own, but it's a very famous song, country music, and that's what will apply to Star as well. He lived to his song because he committed suicide, so he was not old when he died. Forgot how old he was, but he had a lot of issues, so he committed suicide. So he lived to his song, at least. Okay, so any question about stars? Okay, so then I don't know if we're going to get to this. Hopefully, we will. And we will discuss how to find the distances in the universe. And we can go up to just after the Big Bang. So we can find the distance of galaxies just after the Big Bang, just like 400,000 years after the Big Bang, because again, we need to collect light. And during the Big Bang, light could not escape, so we cannot collect light, so we don't know what's going on during the Big Bang. But just after, we are able to collect enough information, so we have ways to find the distances. And if you have the distances, we have way to find the speed. moving away from us, and we have the distance and the speed. You can find the time. So we know like when you look something very, very far away, you know how far in the past it happened. Okay, so remember, farther and farther and farther you look, you go back in time. Okay, so then finally that will be the last unit. We talk about black hole, right? And gravitational waves as well. I don't know if I have, gravitational waves. So that was also 2015. They were able to detect the first gravitational wave. So just in a nutshell, Newton said that gravity, okay, is a force at a distance, and gravity pulls everything together, all the masses together. And then 1905, Einstein comes and say, no. Newton laws, just an approximation. What's really happening is that space around us is some kind of fabric in 3D. So if you think of 2D, it's easier to understand. You have to imagine like a trampoline, right? So 2D, it's easier. Imagine like a trampoline. Trampoline can be stretched, right? So this is my 1D universe, for example. This is a 2D universe. So Einstein said that space is made of some kind of fabric. You cannot touch it, but it's around you, right? It's all around you. And then if you have something massive enough, it's going to curve the fabric of space-time. Like if you have a bowling ball on a trampoline, it will curve the trampoline. So this is what Einstein said. So if you have Earth, okay, it's not really attracted to the sun, like Newton said, it's just being trapped in that curvature, that deep here in the trampoline. If you put a marble here, you push the marble and there is no friction, it will keep here going around. Okay, so that's how he explained the motion of the planets, for example, or the motion of stars about other stars. So if you imagine that space is like a trampoline, and if you have two very massive objects, like two neutron stars, so it's very, 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 very dense, or one black hole and a neutron star, if they orbit each other, what do you think is going to happen? Imagine you have a trampoline net, right, very flexible, and two objects are rotating around each other. It's going to start to make waves, right? So, and that Einstein predicted those waves. They are called gravitational waves, and in 2015 they were detected for the first time, and that led to a Nobel Prize. So I don't know if I have. So it's just an introduction, right? Let's see if I have. I'm losing track. Okay, so here, for example, you have a neutron star. So it's a remnant, it's a corpse, and a black hole. So they orbit each other. They are losing energy. Okay, so that's why they get closer and closer to each other. But they make ripples in the fabric of space-time. So they orbit faster and faster because conservation of spin. It's like a ice skater spinning, going faster and faster and faster. And the black hole ate the neutron star. Okay, they merged together. So with all the new technology that we have today, they were able to detect those waves, confirming what Einstein predicted. So these are called gravitational waves. Going faster, you can see the ripple. That will be the ripple. It's a simulation, of course, but it was observed. It has been observed. Okay. And then, so that is called the wrapping of space-time. I forgot to show you a picture of the sun, just to give you an idea. Sun here, it's rotating. and hydrogen is being burned into helium at the core. And it's a real image. It's amazing that we can get this. So it's a big ball of plasma. So plasma meaning the electrons are not attached anymore to hydrogen. So it's a plasma. Okay. Any question? No question. Okay. So then we'll talk about the universe as a whole. So interestingly, we only know 5% of the universe, meaning we understand stars, we kind of understand black hole, we understand nebulae, which is gas and dust. All those, we get it. But if you take all those, that will provide not enough gravity. So there is something else here. We call that dark matter that will provide that glue stars together in a galaxy, that glue the galaxies together and the group of galaxies together. So it's some kind of glue. And you have theory, you have ideas, but nothing was proven yet. So we don't know what it is. So we call that dark matter. So it's that the glue. And we are thankful for that. Otherwise, if everything move away from each other, we won't be here anymore. It will be very cold universe. So thank you, dark matter. And then you have something called dark energy. So dark energy is because recently in late 90s, they find out that the universe is accelerating. So it's expanding. See, expanding, expansion, this is expansion. But not only it's expanding, that we knew from the 1920s, but it's accelerating. So it's accelerating, meaning it's expanding faster today than it was before. Acceleration means there is a force. Force means there is energy. We don't know what it is, so we call that dark energy. It's like anti-gravity, something that provide anti-gravity. So maybe it's quantum fluctuation. There is all kind of very complex theory, but we don't know. So typical question, universe is about 75% dark energy and 25% dark matter, or 21%, and we only know 5%. We only know about 5%. So if you want to get a Nobel Prize, you can take astronomy as a minor, I'm not saying major, minor, and very hard to find a job in astronomy. So, and maybe you can figure it out, okay? Because Einstein was working as a clerk, patent, right? So he was not even at the university, and figure it out, and he figured out special relativity and general relativity. So why not? So anyway, that will be okay. Video, early universe. Okay, let's watch a video. I'm watching the time as well. If you have any question, let me know. Okay, so that's from the professor I told you about, Alex Filippenko, who was among the teams that discovered the accelerating universe. And if you are interested about dark energy, he has amazing public talks that you can find on YouTube. It's called The Accelerating Universe. Of the universe mostly shows that we have small. So that's a real picture. It's a picture taken very, very, very far away, just after the Big Bang. Just after the Big Bang, you see it's quite homogeneous all over, and you see those hot spots. That will be the seed for the future galaxy. So just after the Big Bang, how do they take this picture? That will be in microwave, right? So it's they are collecting microwave. So it's called the cosmic microwave background. You don't have to worry about it. But basically, it's real data. It's not AI. Okay, my slides are 20 years old, so there was no AI at the time. So believe me, it's not AI. It's a real picture taken of the baby universe.
cold spots. Well, they look small here, but these are actually the seeds from which giant superclusters of galaxies form and the voids between them. And maybe the very smallest ones correspond to what we now observe as big individual clusters at best, but most of them are superclusters and giant voids. And you can do numerical simulations of the collapse of material from these initial fluctuations going over the course of 13 billion years, as shown at the lower left there. That's the time in billions of years ago. You can see material collapsing and forming filaments and clusters and superclusters. In between them, there are voids. And the actual observations of the real distribution of galaxies and clusters in the universe resembles in close detail what we get from these massive numerical computations with supercomputers and with many computers linked together. Here we see things from different perspectives because they've artificially rotated the whole universe, but really we don't think the universe itself is rotating. The sixth big success of the Big Bang Theory is that the observed abundance of helium you map.
So it's before I forget, I need to post an assignment for next week. Okay, I try to post like one assignment a week. And remember, you have two trials. First trial, you really have to try on your own. Second trial, you can look back at your notes. So you have two attempts. If you miss an assignment, I can give you an extension, but you need to ask after the class. Okay? And today we have a pop quiz, and it's open notes. And always give clues about the pop quiz just before the class, just for those who are early, but you should not share. Okay, you don't share and you don't care. Another nice one. So it's based on real data, observations, real observations. So you can see the structure of the universe. You have groups of galaxies and group of galaxies. Maybe we can speed up. So you are zooming out, zooming out, zooming out. Zooming out, zooming out, zooming out. And it's based on real data. That's why it's so interesting, but you get the idea. Okay, so before we start the unit about the scale in the universe, a few definitions. So first of all, do you know that painting? Starry Night, right? Right? What's your name? Huh? Cedric? If you give me your name and you participate, I will remember you for the final grade. But you have to tell me your name and repeat it because I have altogether, I might have 300 students altogether. So I'm trying very hard, but I will never be able to memorize a name and a face. 300 students, that's a lot. So in this class, it's about 70, but I have other classes. So anyway, Starry Night by Van Gogh, right? So very famous. You can see the stars here and the moon. Obviously, the guy was, not quite well in his head. He had some mental issue, but nevertheless, he was a genius, right? He was Dutch, moved to France. He lived in the south of France. And just to connect about history, which is interesting, you know what he did, right? He's very famous. You know what he did? Cut his ear off, right? What's your name? Elizabeth, right? He cut his ear off because he had a very close friend. His close friend was another very famous painter. His name was Gauguin. And they got into a fight. Gog ear. And then he had a picture of himself without the ear. Right? He cut off his ear because he got in a fight with his friend. He got very frustrated. And then he took the ear, wrapped it up, and give it as a gift to a prostitute in a brothel in Paris. So that's for the story. And then he went to a mental institution where he did those beautiful paintings. And at the end, he committed suicide. But now, since 2020, there is controversial. It's controversial. So they are not sure if he committed suicide or it was an accident. But they are still talking about it. So it's a very famous story. And his friend was Paul Gauguin. It's a very famous painter as well. And they were very close to each other. So that's for the story. So let's go back to astronomy. So Van Gogh, the Starry Night. Okay, so few definitions. A star is just a glowing ball of gas. So it's made of plasma. Inside the core, so inside, for example, the sun, okay, it's being squeezed hard enough and the temperature is large enough that hydrogen turn into helium. But you need very high temperature, very high motivation for that to happen. But when it happens, you have, like if you take a piece of coal and a piece of hydrogen turning into helium, you're going to have 100 million times more energy produced for the same amount of fuel, coal versus hydrogen. Okay, so huge amount of energy. So that's the idea of a hydrogen bomb in the nuclear weapons that they use today. So today it's not atomic bomb anymore. Okay, that's passé. Atomic bomb was uranium, hydrogen bomb. Okay, so then you have the planet's definition. It has to be spherical. Okay, it has to orbit the sun, and then it has to clear out its orbit. It means that when a planet is orbiting the sun, it has to be single. There is nothing else sharing the orbit. So that's why they decided to demote Pluto, because you have some junks on the orbit of Pluto. But it doesn't make sense according to me, because if you take Jupiter, Jupiter is sharing its orbit with also some junks. So why did they demote Pluto and not Jupiter? I think it's not fair, but that's my point of view. So anyway, if I ask you for a test, we have 8 officially, but it's still controversial. We have 8 planets and not 9. So the way I used to remember, my very educated mother just served us 9 pizza. So you have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. But now is what? Nothing. Serve us nothing. Okay. So then you have, so for example, here you're going to have Jupiter with its 4. The closest moons are called the Galilean moons because they were seen, observed for the first time by Galileo. So it's a beautiful picture because you have the moon and the shadow of the moon, right? And then you have a definition of a moon. So if it's lowercase, it's not our moon, it's just a moon orbiting a planet. If it's our moon, it has an uppercase. So this is the moon with an uppercase because such important moon, right? So we'll finish that next time. I will upload the lecture